Okay, shall we get started then? So in my second lecture, I want to talk about another model with strong interactions. This is the Ising model, but in two space dimensions. This has also been studied a great deal, and I'll refer to some of the old work, but I'll try to point out especially that once we consider quantum dynamics at finite temperature, it's still many things need to be understood. And the new generation of experiments that are now coming online, even for this very simple model, can teach us a lot. Okay. So in one dimensions, the Ising model itself is can be written in terms of free fermions, and so many things are much better known. But once you move away from the free fermion description and some non-integrable limit, that's still problem of some interest today. Okay, so let me begin by something you'll hear much more about in Antoine Brouet's lectures later this week. Because finally, I mean, the Ising model was actually, when I wrote my book on quantum phase transition, I had several chapters on it, but nobody was really studying, especially its finite temperature properties in those days, because there was really no clean experimental realizations. Then Radu Koldia, after many years, found something in one dimension in cobalt niobate or something like that. And that led to some very beautiful experiments. But now we finally, after a long wait, have something that's very clearly the Ising model in two dimensions. Okay, so the basic ingredient are these optical tweezers in which you put a Rydberg atom, and then by shining lasers on it, another set of lasers, you can take it either in the ground state or some highly excited state. So there's the ground state, and that's the excited state, and these are the G and the R states. So there's a laser that, actually two lasers that connects this state to that state, and this is the Rabi frequency of the off-diagonal matrix element that takes you from the ground state to the excited states. Then, what is this? Oh, yeah, well, these are the same things. Okay, so this is what's called, oh yeah, this is on this delta is what's called the detuning. So what's happening is that you have some ground state here, and then you have some Rydberg state up very high in energy. Then you send in a laser, and the amplitude of this laser determines the Rabi frequency omega. But there's this laser is resonant with some other level over here. Once you put in the laser, you get some energy here, and the detuning is this spacing. So that's a very small energy level, energy spacing, compared to this, which is way in the optical or ultraviolet. But when you go into the rotating reference frame, you can forget about the laser and just imagine that this ground level is actually just a little bit above or below the Rydberg level. Okay, and they call it red detuning and blue tuning, whether that level is negative or positive. Okay. But we are going to just go into this rotating reference frame, just think about it as some equilibrium system. So then here's our Hamiltonian, where the relative energy between the Rydberg state and the ground state is just delta. Yeah, so delta positive, I guess the sign I've chosen here is the Rydberg level is below minus. So this would be minus delta in this notation, I guess, because then if you go on this side, then the Rydberg would be below the ground energy, so this should be minus delta. Okay, but then, so that's just all for a single atom. But what's remarkable about these Rydberg atoms is that the Rydberg states are really huge. So if one atom is in the Rydberg state, and the other atom is in a ground state, then they don't even feel each other because the ground state is tiny. However, they're both in the Rydberg state, then they start interacting. So that's how you can entangle them, because the interactions between them are really sensitive to which state you're on. And this is what leads to, that's the key trick to use this for various quantum computing type operations. You may have heard many papers recently by both Broways and Misha Lukin's group. They moved on to another scheme for encoding the qubit that has to do with taking some hyperfine levels of the atom itself. But they still need to, to transfer quantum information from one atom to the other, they still need to excite it to the Rydberg state so that they can feel each other. So the Rydberg then becomes kind of a bus for communicating, but that's not the way I'm going to use it here. Here, the Rydberg is actually part of the qubit. Okay, so here's another view of it. These are the two lasers. And then, okay, so now I've written it slightly differently. I think of it as a model of bosons, which is a model we were playing with many years ago for somewhat different reasons. So if it's in the ground state, we say there's no boson. If it's in the excited state, we say there's a boson. So the Rabi frequency here can take you from the ground state, from the excited state to the ground state or backwards. So that's this operation. This is if you're in a Rydberg state, you gain energy delta. And this is the repulsion between these bosons. So these are hardcore bosons. Can only have one boson on each side. And then they repel each other on nearest neighbors. So this was a model, in fact, in this particular paper with Paul Fenley, we found various limits of this model that were integrable and some very complicated phase diagram in one dimension. And there's several papers on one dimension on this, but I'm going to focus on the case of, two dimensions. Let me also just mention, there's another model you may have heard about a lot, something called the PXP model. And the PXP model is just a special case of this model where you disallow, where V1 is infinity. So basically, nearest neighbor sites can't both be in Rydberg states. And then the other interactions are zero. That is exactly the PXP model. And in fact, precisely this model was diagonalized already in this paper in 2002. We didn't call it the PXP model. Anyway, so this is a more general version of the PXP model, and the PXP model has been a lot studied for very interesting properties, both in 1 and 2 dimensions. Okay, but here I'm going to focus on the case of this Rydberg atom on a square lattice. So this is the theoretical calculation by Ryan Samajdar, my former student, as a function of, this is the detuning, I believe. The delta now has become small delta, and this is the range of the interactions. Okay. So it's not just nearest neighbor, the interactions fall off as 1 over r to the 6th, as you can see. That's the van der Waals interaction between the different atoms. It only acts when your nj is both 1. So you just take this model, put the tweezers in a square lattice, and ask what happens. So if your detuning is small, everything is in the ground state. And then you start increasing the detuning, and as you want to put them all in the excited states. And then now they all can't be excited because if they're nearest neighbor, there's too much energy to pay from the repulsion. So depending upon the range of the interaction, you can get really an amazing rich variety of states. This is the density on each site. And I'm going to focus on this checkerboard state here, which you get for small range of interactions. So if you really try to make all the atoms in the Rydberg state, only half of them succeed, and you get a checkerboard pattern. So this pattern has a broken symmetry because which half are up and which half are down? Well, if you have an infinite lattice, either any could be there. Here, probably things on the edge or some effects, always pick one, or your initial condition, actually. You can pick some initial condition. And when you see the checkerboard, there's a checkerboard state. And there's many other more complicated patterns you get with longer range interactions. This has also been studied on the Kagome and the Ruby lattice. And there's possibility of even some spin liquid states somewhere. But I won't going to talk about that. I'm going to focus just on this very simplest case of a checkerboard lattice. So this was the theory prediction, this kind of phase diagram by DMRG work by Ryan. And then this was the experiments. Again, I won't go into the detail of all the experiments. They found essentially all of those phases. I'm just going to focus on the checkerboard phase. So in the checkerboard phase, then, this phase transition, here there's no broken symmetry, and here there is a broken symmetry because depending on whether the Rydberg atoms sit on the black or the white squares. Yes?
Sorry, the color is?
It's the density, basically. The probability of occupying the Rydberg state or the ground state.
Ah, okay, yeah, thank you.
The density of the hardcore boson, if you want to think of it, or the probability of being in the Rydberg state. Something like that. Oh, in this plot, what is the density? I don't remember. I have to ask. Yeah, I've forgotten. But in this picture, yes, it's just the density. What is the color here? I don't know. Here is the density. Yeah. Thank you. Yes, it's probably the entanglement entropy. And so that becomes very large near a phase transition, so it allows you to identify. Yeah, thank you. That's probably what it is. Okay, so when I'm going from here to here, there's a broken Z2 symmetry. So this then is a realization of an Ising quantum phase transition in 2 dimensions with a broken Z2 symmetry. And it's really the first time anybody's seen such a clear quantum phase transition of an Ising system in 2 dimensions in any system that I'm aware of. Okay, so let's see. So here's let's see, is this the more recent experiment? No, this is the old experiment still. So this is looking at the checkerboard pattern a little more carefully. You can see that this is the experiment. This is the observation of, I guess these are the 2-point spin correlation function. And you see a beautiful checkerboard pattern with a long correlation length. These are actual snap. This is not a picture. These are actual pictures from the experiment. But you just measure every atom and see if it's in the up state or the down state. Occasionally you have some defects. And then from these thousands of these pictures, you can compute a correlation function. And from the correlation function, you can get a correlation length. And what they saw was, okay, there's some subtleties here with Kibble-Zurich scaling that I'm not going to go into. But they see some increase in the correlation length as a function of detuning. And they also look at how quickly you scan the detuning, how that affects the growth of the correlation length. That's called Kibble-Zurich scaling. And from that, you can read off the 2 dynamic critical exponents, which is nu, and this dynamic critical exponent. For the Ising model, Z is supposed to be 1. I will derive that in a few minutes. And nu is the value that you get from, in those days, the epsilon expansion was the best value. So their best estimate was 0.62, which is pretty close to the expected value for the 3D Ising model. And I'll discuss why this is the same exponent as a 3D classical Ising model. Okay, this is the more recent experiment, and they're still ongoing. This is now looking at the dynamics of the phases. So there's a lot in this paper, which just came out this year, in February of this year. And in particular here, what do they do? They start out with this particular state. So this is a fully polarized state with one sublattice with the Rydberg and the other in the ground state. And then they just let the thing evolve, okay? At different values of the, I guess, yeah, this is the time evolution, and the color is the different values of detuning. So there's a critical detuning where there's a quantum phase transition. Okay, so if you're way down here, which is where you're deep inside small detuning, where there's no long range order, then when you see the thing evolve, the average value of the order parameter, you see it oscillate. Okay, so now what are these oscillations? Well, as I'm going to derive, there's some kind of, you can write down some Landau-Ginzburg theory. So there's some order parameter. You have a Z2 symmetry, so if you didn't know anything else, there's some potential for the order parameter, V of M. It has to be equal to V of minus M. So you say, well, V is equal to alpha M squared plus beta over 2M to the fourth. And then alpha greater than 0 means you're disordered. And alpha less than 0 means you're ordered. So let's imagine alpha is greater than 0 because that's small detuning. So here's your potential. It looks like this for alpha greater than 0. And this, so if you had a particle, it's like a harmonic oscillator at 0 momentum here. The magnetization, it would just oscillate back and forth. So that's the oscillation here. Very nice oscillations. So at this point, they're only measuring the frequency. It'd be very nice to see the damping. The damping presumably comes from some finite temperature effects or the fact that the initial state is not perfect. I don't know, laser noise. I mean, these things need to be understood. But right now, if we just focus on the frequency, you see this high frequency here. And then as you get closer to the critical point, as you move towards the phase transition, this becomes flatter and flatter, right? So this potential, when you're far from the critical point, looks like this. Then as you get closer to the critical point, it becomes flatter. But sorry, I'm not drawing that very well. And then eventually it turns down and then turns back up again. So what they see is that the frequency, there's some fits to all of this. And this is the red line is the frequencies that they measure. They go down as you approach the critical point, but then it goes back up again. And that's when you have the inverted parabola, then you're sitting either here or there, but you're starting on one side. You start over here, and then you're going to oscillate over here. And that frequency will also go up. Okay, so that's sometimes called the Higgs mode. Okay, you can call it an amplitude mode. It's sort of like the Higgs particle, except there's no gauge field here. So some people get very upset when you call it the Higgs mode. Other people say, okay, go ahead. I don't know. I think it's better not to call it the Higgs mode because the Higgs mode really is a property of a gauge theory, but there is no gauge field here. It's an
massive Goldstone mode, right?
No, it's not a Goldstone mode.
No, but it's a massive part of the Goldstone. It's a transverse Goldstone.
There is no Goldstone mode here at all. This is an Ising model. Okay, let's not get into semantics. Some people call it the amplitude mode. Some people call it the Higgs mode. Fair enough. Okay, what I want to focus on is something very interesting. And I will at least go part of the way in deriving this result. I end at what time? 5:30? Hopefully I'll end even before. Okay, we'll see. All right, so what you do, so you pick a number X, and you measure this frequency, these frequencies, when delta is bigger than delta C. So that would be on the Higgs side. And then you pick a frequency which is delta is less than delta C. That's also equal to X. So you take equal this side and this side equidistance in any parameter you like. Could be the detuning, whatever. You just go equally on the two sides. And then you look at the ratio of the frequencies, the ratio of this frequency to that frequency on symmetric sides of the critical point. So, okay, so then they did this. I didn't tell them what the answer had to be. They got 1.9. Okay, I mean, the data is not the greatest, but I think this needs to be studied a lot more. Anyway, so this number is in fact a number that's a property of a relativistic quantum field theory, or in fact, has been computed in various epsilon expansions. I will present to you a very simple theory just based on that polynomial, which says that the number should be square root of 2, which is 1.4. This is far from it, but there are corrections that come from the fact this is a strongly coupled field theory. And this is one of those rare cases you can actually compute these corrections quite accurately. And the number is around 1.8, 1.9. So that is the theoretical predictions, which is being tested by this dynamics. Of course, what I would love to do, but at this point, I don't think they have enough resolution, but I know the next generation of experiments by Tom Manowitz will look at what happens right near the critical point, how things depend on the energy density and the temperature, and where things, do they oscillate, do they relax? I think there's a lot to do, all right. But it's nice to have a real, a clean example of a strongly interacting quantum critical system where you can study real-time dynamics. Okay. And so Anusha, you were telling me something before my talk. So you can explain part of this too? I'm not saying two. I mean, can you? Yeah, go ahead.
I'll talk about it on Friday, but we understand this as being not a consequence of the quantum critical point, but a dynamical phase transition in the ferromagnet, which is what I'll talk about.
You mean, but in the paramagnet?
Yes, so which
Okay.
we have.
This same data?
Yes, yeah.
Okay, all right. Unfortunately, I won't be here, but okay, I look forward to, I'll try to watch it online. All right, but okay. But let me present the theory as it is of the Ising model. That's what I'm going to do in the remainder of my talk. Okay, so we're not going to work with the Rydberg model. I'll work with the canonical Ising model of just qubits on some d-dimensional hypercubic lattice. Let's just take nearest neighbor couplings J, and then a transverse field will be J times G. So now we just tune the value of G, and there's a quantum phase transition at some critical value in any dimension of this model. We're interested in, especially in the model in 2 dimensions. Okay, so let me just talk about this as more rather than a phase transition person, but a quantum person who just knows how to do perturbation theory. And the nice thing about this model is that there are 2 different perturbation theories you can do, depending upon G being small or G being large. So first, let's take G very large, G much greater than 1. Then there's a unique ground state, which we call the quantum paramagnet, where the spins are pointing. So here I should have said the Z's and X's are just the Pauli operators. I'm not using sigma Z and sigma X, because that's one good thing the quantum computing people have taught us. Drop the sigmas. Okay. So this is the eigenstate of the X operator. And so the X operator is just the linear combination of up and down, and the left operator is up minus down. And the ground state doesn't break the up-down symmetry as all particles in the X. That's the ground state. Okay, what about the excited states? Well, there are n excited states which are degenerate, at least at G equals infinity, where you flip one spin and make it point in the minus X direction. So yeah, exactly at G equals infinity, you have n-fold degenerate states here with energy G. Is that G? Yeah. And then what about the second excited states? Well, you flip 2 of them, and there's an n into n minus 1 over 2 states there, which are all degenerate, and so on. All right, but G is not exactly infinity, so you do 1 over G perturbation theory. So what happens at order 1 over G? Well, here you have, this problem has a translational symmetry. So all the states have to be eigenstates of momentum. And so if you look at the ZZ operator, what it does is just hop this particle either to the left or the right. So you just get essentially a tight binding model, okay? You get a tight binding model, yeah, here it is. And the exact eigenstates are simply, if we flip the spin on this state, I'm going to call I, you just go to momentum space and you take the states, which are momentum superpositions and momentum K, and then to order 1 over G, that just gives you a tight binding cosine model, and that tells you, so now each of these states is non-degenerate for each momentum K, so you just have one state for each momentum K, and those are the one particle states here. So they get a bandwidth which increases, and there's one state at each momentum K. Okay. Now when you go to, what about the next set of levels? Well, the next set of levels have two flip spins. Now you have an infinite system, and one spin is here and one spin is over there. They don't care about each other, and their energies will just add. So you will just get the so-called two particle states, each labeled by their own momentum. But then, if these are momentum states, they will feel each other. And the individual momenta of the two particles are not conserved. So only the total momentum is conserved. So for each total momentum K, there are many, many states. So now you get what's called the two-particle continuum. So if you were doing some scattering experiment, say you were measuring the following correlation function, you're measuring dr, dt e to the I k dot r minus omega t, and you're measuring z of r and t, z of r and 0, 0, 0, 0, 0. So neutron scattering would measure something like this, which you'd call the dynamic structure factor. Various signs and so on, I won't worry about. And so what will the structure factor look like in this phase? Well, as a function of omega for a given k, you will get a delta, you would actually get a delta function, an exact delta function, which will be delta of omega minus ek. So independent of whether the model is integrable or not, in any dimensions, provided G is large enough, and you went to 0 temperature, there will be an exact delta function here. This is sort of like Fermi liquid theory. In Fermi liquid theory, there's an exact delta function only right at the Fermi surface. Here, it's much better because the system has a gap, because there's a gap here between the ground state and the first excited state, even for a finite G, because there's a clear gap. The quasi-particle, this is the quasi-particle, is infinitely long-lived, strictly infinite, okay, for a finite range of momenta, not just at the Fermi level or something. There's some residue here, which we can worry about, which you can call Z, will be delta of omega minus k times Z. But Z is just 1 at G equals infinity, and it'll have corrections of order 1 over G. I'm computing those as an exercise in my book somewhere, I think, but don't ask me to do it. Okay, then what happens? Well, if you go to higher order, now it turns out this thing has a Z2 symmetry. So in fact, you can't create two particles out of the Z operator. You can only create an odd number of particles. So the next set of excitations would be the 3 particles that you would create by the Z operator in the ground state. This is all at 0 temperature. Of course, at finite temperature, this will have a width, and it's a very interesting exercise to compute that width, which you can do by, as you can imagine, by just a classical Boltzmann equation, actually. But going back to 0 temperature, there's going to be, for each momentum k, so now you're injecting momentum k and creating 3 particles. So previously, you inject momentum k and you created 1 particle. Now, each particle has a very definite dispersion, even though there's not integrable, it has a dispersion that you can compute to any order. Then when you inject momentum k and you create 3 particles, now it's up to you how you're going to divide that energy between the 3 particles. There are many ways of dividing that momentum, sorry. You're injecting momentum, fixed energy omega, and fixed momentum k. You choose how you want to divide the momentum into different momentum. So you have k is going to be equal to k1 plus k2 plus k3. So this is the state you create, and these particles run off to infinity. And then the omega will have to be E of k1 plus E of k2, E of k3. So this is exactly the single particle states that you create. And fixed k gives you many possible omega. So you get what's called, I don't know the shape of it, but you can try to compute it. You get a whole spectral function here, and you'd call this the 3-particle continuum. And we well separated from here, provided the gap is large enough. And you can keep going, and eventually there will be also a 5-particle continuum and so on. There's an infinite number of continua. Some of these have been seen in some experiments in the dynamic structure factor. Okay, and this is all very general structure independent of any integrability. It's also true for the integrable model, but it's also true for non-integrable models. Now, sometimes what could happen is that the 3 particles could form some strange bound state. Instead of scattering off to infinity, they could form a bound state. And that could give you additional delta functions. Maybe there's a bound state here. There could even be anti-bound states here. There could be some other delta functions around, depending on this particular model you're looking at. But the lowest one will be just a particle, and then you can have other bound states or scattering states. You just have to solve the problem order by order in 1 over g. Okay? So everything I've said, you can deduce just by doing the perturbation theory you learned in your first quantum course, order by order in 1 of g, gives you this entire picture. You just have to do it in an infinite system, and it's a little tricky, but that's make n finite and then take the infinity limit when you consider the right observable. Okay. All right, so that's for g goes to infinity. What about when g much less than 1? Now, in some ways, things are very similar, but some ways are very different. So now you have 2 degenerate ground states, all spins up or all spins down. So it's degenerate. And so there's no simple way you can connect this to the g much bigger than 1. And so there must at least be one quantum phase transition. And really the whole interest is to find out what happens near the critical g. Okay, so let's pick a ground state. Say this one, a break symmetry is broken. We are working with this state. Then what is the, again, there's a particle-like excitation, which is just one flip spin and has some energy, which is quite a bit bigger here because you have all these broken bonds. And you can break 2 of them. And in fact, you can see here that there is always a 2-body bound state because they like to be less surface area and so on. But there's one thing special about 1 dimension, which doesn't happen in higher dimensions. In 1 dimension, if you flip a spin, then that flip spin can split apart into 2 domain walls. So the energy of this configuration and this configuration is exactly the same because each has 2 frustrated bonds. Here they're right next to each other, here they're far apart. So in fact, this flip spin fractionalizes into 2 domain walls. And these domain walls behave like free fermions. So that's what the fermions are in at least one of the fermions in 1 limit. These are the fermions. So 1D is very special. In 1D, in fact, if you did this kind of experiment on the ordered side, you will not see a delta function. You will see a 2-particle continuum because even a single particle flip creates 2 particles that can run off to infinity. So it doesn't happen in 2D, it happens in 1D, at least for this model. Of course, there are interests in much more complicated models where it happens also in 2D. These are spin liquids and so on, but that's not the topic of my lectures. Okay. So here, in fact, there's even a little subtlety, let's go to 2 dimensions, go back to 2 dimensions, and try to do perturbation theory to determine the dispersion of this flip spin. And when you try to do it now, you run into some strange behavior. So for example, you could start with this state, and you're doing perturbation theory to make the state move, this guy move. Well, you could imagine that, so you flip another spin really far away. Okay, if you flip this other spin really far away, and that's the intermediate state that has two particles, and then you unflip this, and you get you seem to have moved this particle from here to anywhere you want, 100 sites away. That seems very crazy. But then you realize there's another way to do it. You could get rid of this, and that takes your energy below, which is also allowed when you do the perturbation theory. If you're looking at the correction of the energy of an excited state, you should sum over all other states, those above and those below. So this has a negative gap, and then you could create it 100 sites away. So there's two ways of going from a spin here to there. And it turns out these two processes cancel each other, because one has an energy gap, the other has a negative energy gap. They cancel. So in fact, in the end, the problem is local. You can't just jump from here to infinity. It's just not allowed, or it just cancels because of the two processes, except for the nearest neighbor, where you find it doesn't cancel, because the number of neighbors change. The two processes don't exactly cancel. Yes? No, because the perturbation is with the X operator. The X operator can act anywhere. This is a perturbation theory in G. Sum over X, so just in perturbation theory in Z, you can pick any X you want. The other case was simple because it was perturbing by this, ZZ, that's nearest neighbor. But now it looks highly non-local, but it isn't. And the reason it isn't is because of the cancellation between going through an excited state as opposed to going through the ground state. This is also a very general thing that happens in many systems. The Hamiltonian is local, the particle-like excitations also move locally. But for a while you get confused when you try to do the calculation. So it's a little more subtle here to get this number C, because it involves some cancellations, but you can do it. And again, you find it's only nearest neighbor hopping, and so you get a very similar dispersion. Okay. All right, so you've done a calculation for large G, and you found a gap that decreased. That was this number here. So the minimum possible energy is at K equals 0. There's some decrease in the gap. I don't know, put K, I forgot. Anyway, there's a decrease in the gap as you decrease G. Starting from here, the gap goes down. This is the gap to the smallest possible single particle excitation. And similarly, it goes down here. This is all valid for very small G of a very large G. We know there has to be something dramatic happening, and the question is what, okay? So this is not something it's so easy to express by perturbation theory. You have to use some tricks to figure out what's going to happen in the center. So now I'm going to argue through some tricks that both gaps vanish at the same point. It's not a fine-tuning thing that always happens, that they vanish at the same point. And in fact, they vanish with some power law. And this is how we define this exponent as Z nu is called for historical reasons. And then I'll define what Z is a bit later. And so then in turn that defines nu. Okay, so how do we show this, that this gap vanishes in this way? Okay, so this relies on a concept that's been long developed in the theory of classical phase transition, idea of universality, that we have a transition between two different states here. These are quantum states, though. One where the symmetry is not broken here, to one where the symmetry is broken. And here there's a gap, and there's a gap. And how are you going to go from symmetry broken gapped state to a symmetry unbroken gapped state? So the idea is there's a universal way to do it, and you could use other systems which have the same basic feature. Okay. So let me begin that way, and then you'll see why this is somehow related to the Ising model. So I'm just going to cook up another model for now, which has the same feature that has two gap phases, and then they're supposed to meet somewhere in a phase transition. And the advantage of this model, of course, will be it gives me a different perturbation theory, which also works near the phase transition. The Ising model, I don't know. Just by working with the Ising spin, I don't know how to get any kind of perturbation theory near the critical point. Okay. This perturbation theory has its own problems, and of course, many brilliant people have over the years worked on trying to cure it. Many Nobel Prizes are given on how to cure the problems with this theory. But okay. All right, so here's the problem I'm going to take. What I'm going to take is on each site, I'm going to have a nonlinear oscillator, some fictitious oscillator with coordinate phi. Okay. What is phi? I don't know. It's some fictitious oscillator in some other space. I'll identify phi with something physical soon for the Ising model. Okay, so this is some canonical, this is the momentum of this phi, and there's some V of phi that looks like this, okay? Okay, so it'll always have this inverted parabola shape. So it has two low-lying states, the left state and the right state. And of course, you can tunnel between them, and that will lead to an energy gap. So I'm going to call this state, where it's on the left well, as the down state of my Ising spin, and that state as the up state. And this is the tunneling between them, delta. So in fact, if I just have one oscillator with these two states, then the ground state, which I'll call the right state, is the symmetric linear combination. The other is the left state. And so if I only pick these two states, those are the eigenstate of the X operator, okay, in terms of these up and down. So I have a qubit that I create out of this nonlinear oscillator, and I've told you what the X operator is. It's just what appears in the Hamiltonian. Its coefficient is the energy gap. Okay, what is the Z operator? Well, let's look at the ground state and hit the operator phi on it, okay? So this will give me some other wave function of this oscillator, which is, so this was the up state and the down, psi up and psi down are these parabolas over here. So when I multiply it by phi, this becomes an odd under phi goes to minus phi. So just by symmetry, then I can now look at the matrix element of the operator phi between the left and the right states. So right is 0, left right is 0, and this is some complicated matrix element, which I'll call non-zero. Okay, so what is the operator in the qubit basis that takes it from left to right? Well, that's just the Z operator, okay? So phi is just like the Z operator. The displacement of the oscillator is like the Z operator, and the N in Hamiltonian is just the X operator. Okay. So this is a lot of work to get one qubit. But believe me, I mean, this is what you do in the superconducting qubit. So literally, phi, in that case, is the flux through the superconducting qubit, and that's how you get your qubits. Okay. Here I have exact symmetry between up and down. Okay, now I'm going to couple these oscillators together with this coupling J. And this nonlinear oscillator, I'm going to now project down to the qubit level. And so phi projects down to Z, and then I get, lo and behold, my Ising system, okay? All right, so what I claim is that at low energy, this particular problem, I can explicitly map it, get all the numbers and everything correct to this Ising model that I'm interested in. Okay. So why take all this trouble? Well, because in this approach, I can do yet another perturbation theory. And the perturbation theory I can do in this approach is the non-linearity in this potential. So this is if it's just a harmonic potential, well, I have nothing to do, but it's a non-linear potential. and I can still work with it. I can work with the nonlinearity. The quartic term is going to be my perturbation expansion. Is that going to work? Well, not really, but let's just go ahead. You have to invent the renormalization group then to make that work. That's literally why the renormalization group was invented. But okay, so you can still go a long way. You're just using mean field theory. Okay, so I just take the usual Landau-Ginzburg potential for phi. I had taken R to be negative, but now I'm just going to let R run from positive to negative. And just think of this problem as a problem on its own and ask, does it have a phase transition? And if so, does it have the same basic feature as the Ising model? And then can I use it near the critical point? And the answer is yes, you can. Okay. All right, so here, we do something. First of all, you go to momentum space. Then this phi I, phi j becomes just some constant minus k squared at small momenta. So then you can go back to real space and write it as, go back to some continuum limit of momentum and displacement operators. And then finally, you get what's called the phi-4th quantum field theory. So now phi is a quantum field in space and time. This grad phi squared comes from here. This k squared term gives you the grad phi squared. The R has been renormalized a little bit. But here's another theory, which at least in some limit, I can explicitly map to the Ising model. But now I can, after all, even the Rydberg model, Hamiltonian was not the Ising model. It was something quite different with broken translational symmetry. So if you really have to work through that, if you believe the Ising model describes it, you should believe this also describes it. It has the same basic feature of a Z2 symmetry. And now the tuning parameter will be R. And amazingly, this will give us a behavior for both even at the critical point. It'll allow us to go from far to the critical point to close to the critical point, provided I can do perturbation theory in U. Okay. Any questions on this quantum field theory? Okay. All right. And this phi and pi are just canonically conjugate variables. Okay, so now we can just do mean field theory. So that's the beauty of this theory. And we previously had to do some complicated perturbation theory. You just do saddle point. Just do saddle point, what do you get? Well, okay, so when R is positive, you have this potential. You can compute the fluctuations. It's just a Gaussian oscillators. And you get this dispersion, EK, R plus square root of t squared. And that is my quasi-particle. That is exactly this EK. I have a value of EK, which is quadratic dispersion. This is the quasi-particle. That is, I identify that with the phi particle. The phi field creates or annihilates this particle. So phi is A plus A dagger, where A is the annihilation operator and the creation operator, just like displacement in oscillator, X plus A dagger. And pi is just like the momentum of the oscillator. So now we have, okay. But now this seems to be valid, provided I ignore the U, all the way down to R equals 0, where this becomes infinitely flat. And so this tells me that the gap vanishes as square root of R. Okay. How about R less than 0? Well, now I have a broken symmetry with the inverted parabola. Again, I do fluctuations about this point. And then I expand about this point, and I get this extra 2 mod R there. But you get some particle, just like I found in the particle for small g. And the dispersion now is k squared over plus 2 mod R. The U drops out. Yeah, so the funny thing is here, I need the U to find this minimum. When I expand about this minimum to quadratic order, please do that calculation. The U drops out at quadratic order. So the curvature here is independent of U. It only depends on R at the minimum. Okay. But the extra factor of 2, so that gives you delta is square root of 2R. So this is the gap then. For R positive, there's a small gap, and this is the large gap. And that's supposed to be this picture. And this f of x is square root of 2. So the square root of 2 is just the ratio of the curvature here, or the square root of the curvature here to the curvature over there. This is flatter, and this is, has more curvature, so the energy is higher by exactly the factor of square root of 2. Okay, so not bad for a very trivial theory. It's not so far from 1.9. Okay. Yes. Yeah. Yes. Yeah. So, okay. So, yeah, that, for that you need the epsilon expansion and the renormalization group. I certainly can't do that in half an hour, but I can try to tell you a little bit about what you do. Okay. So you take this theory and, so here let me do it on the ordered side for r greater than 0. So right now you compute the Green's function, G inverse, it was k squared plus omega squared plus r. And then you get a correction from the self-energy. There's this term which actually, and then there's the next term which is graphs like this. So this is u and this is u squared and so on. And then you evaluate this. And when you evaluate this, you find there are certain, as r goes to 0, there are certain infrared divergences. So anyway, so you find, and then you look for, you take this theory with a finite cutoff, shall we say, and you look for g of k equals 0, omega goes to I omega. So this is imaginary frequency. Then you take the real frequency limit and you look for poles of the Green's function. When you do the calculation on the ordered side and the disordered side, you look for the poles for the Green's function, and then you look at the ratio of the poles. And then when you look at the ratio, you get an answer which is square root of 2 plus some number of order u in appropriate dimensionless. U is not dimensionless, but I'm just being very quick here. Then you have to remember that near the critical point, u goes to what's called a Wilson-Fisher fixed point. And then you put the Wilson-Fisher value here, and that gives you the corrections. Okay. Yeah, so there is a renormalization scale, but the dimensionless is precisely there's a dimensionless u coupling G, I often call mu to the epsilon times u, and then beta, you look for the solution of beta of G equals 0, the beta function, and this is just, you put in the value here, and you get a number. And so that, I don't have that's, not, I want to talk about something else, but okay. That really relies very deeply on the scale invariant structure of the critical point. It's one of those dynamical quantities you can actually compute, and also, well, claims to have been measured, although Anusha may have other opinions on that.
So we said in one dimensions that the quasi-particles are, like for the one-dimensional Ising model, are two separate Majorana fermions, right?
Yeah, whose energy, I mean, you can write it as the same Majorana fermion.
But when we write the field theory for it, it looked like we're using bosonic fields.
For which?
For the Landau-Ginzburg type action.
Yeah, so.
Is there like a hidden bosonization happening there?
Right, so in one dimension, if you take this field theory, it's related to this, So in principle, you could take this field theory in one dimension and try to analyze it. It's not integrable or anything. And you try to do perturbation theory in U, and it just totally breaks down. Okay. So the way you understand, so if you take this theory this has certain soliton solutions when R is negative. Okay, so this has solutions when R is negative, so you have some potential. This is V of phi. And as a function of X in one dimension, you could have a solution which is either here or not there. It could have a domain wall solution. So these are the soliton solutions. It goes from here to there as a function of X. Okay, and you just focus on these solitons, and then you look at the behavior of these solitons and how they scatter each other, and compute their S matrix. And when you compute the S matrix of this soliton, you find it's exactly -1, excuse me. So these solitons behave like free fermions at low energy from this theory. So it's not an exact transformation, but you can recover the free fermion description from the fact that these solitons have S matrix -1.
Okay, thank you.
Yeah, so that's how you would connect them. So in 1D, the fermion picture, so if you 1D have this fermion, although, like I said, you don't measure the energy of the fermion in this as simple a way by just looking at the delta function. But in 1D, if you look at EK, the gap of the fermion as a function of coupling G, it vanishes linearly, and in fact has the same amplitude on both sides. So this number, which is square root of 2 in mean field theory, in the free fermion theory is 1. So this same experiment in one dimension, if you measure the gap appropriately, would give you a ratio which is exactly 1. And it's quite different in 2 dimensions. It's supposed to be near 1.9. Yeah.
Hi, so I just wanted to ask about the color plot for Rydberg atoms on the square lattice.
The what, sorry?
The color plot in the beginning, like I just wanted to ask why the checkerboard is at RB over A equals 1.2. What does that line signify? Yeah, this one.
This is the theory plot.
Yes, so what does the 1.2 that line signify?
I've forgotten, but I suspect there's some data in some other plot along this line. That's probably why we drew it there. There's another plot which is plotted along that line.
All right, okay.
So it doesn't have much meaning, I think. All right, so now we're all experts, at least in mean field theory. Oh, yeah, I guess should have mentioned this here. So I kind of implied this. So this is a 2+1 dimensional relativistic field theory. Why is it the same as a 3D Ising model? Well, that's really trivial to see in the path integral representation. You just take the imaginary time path integral of this quantum field theory here, this quantum field theory, write it in imaginary time. So there are d spatial dimensions. And when you go to imaginary time, this pi phi just becomes d phi d tau squared. That's just the kinetic energy in imaginary time. The mass is 1. So that gives you this. You can put a mass here. I don't know why. And so that theory, if you look at it, where is it? Yeah, here's the theory. There's a time derivative and a spatial derivative. Now they come in exactly the same way. So you can just write it as d mu. And so the low energy theory near the critical point is a relativistic field theory. And now you can interpret it in 2 different ways. You can think of it as a relativistic field theory for a quantum model, Ising model in 2 space dimensions, or as a classical field theory for the classical Ising model in 3 dimensions, which is the way it was usually interpreted in the old literature. But now we are starting to think about, given such experiments, what does this field theory look like in 2+1 dimensions? Okay. So that's really about the ground state and the first low-lying excited states. All this discussion has been about that. Single particle excitations about the ground state and how the ground state has a quantum phase transition. So to return to my theme of my lectures, is really about finite temperature. What happens at finite temperatures? So then there's this generic kind of phase diagram one can draw. For the phase diagram as a function of the coupling G, now I'm back to the Ising model, so all we've been studying so far is this line at 0 temperature at some critical point GC. Now I'm going to raise the temperature. So where does temperature appear in this field theory? Well, if you ask, if you're sufficiently low temperature, it only appears at one place. It appears only in the fact that there's periodic boundary condition in temperature where beta is 1 over temperature. That's the only place there's temperature in this field theory. So that's like a finite size effect. So that means that if I'm thinking in classical terms, I said that the ground state property is mapped onto a 3D classical Ising model at some other temperature. That's not real temperature as far as we are concerned. Then if I put a temperature in the quantum model, it corresponds to taking my 3D Ising model. So I have a 3D Ising model. I can't go outside those lines because the cameraman is not here. So I have a 3D Ising model, and so it has some spatial extent, which is L, which is going to go to infinity. And this is also L. But now it has a time direction, so this is time. Something like that. And this is going from 0 to beta. And then the top side is periodic boundary condition. The top side is connected to the bottom side. Okay, so as far as the classical person is concerned, the geometry of space is R2 cross S1. And the circumference in the time direction is the temperature. So in classical physics, I'm doing finite size scaling. Okay, so that, classical physicists have done that. They understand a lot about Ising model in finite boxes too. You can read whole books on finite size scaling and so on. And people have done all kinds of calculations. So you would think, oh, I'm golden. I'm going to get all my quantum properties at finite temperature very easily. Unfortunately, there's a small snag, and that's the snag of analytic continuation. So the problem is this. So what are the allowed values of the classical frequency, if you wish, or the wave vector in the time direction? So the wave vector in the time direction is my imaginary time. This imaginary time is like the Matsubara frequency. So the wave vector in the time direction, or the values of omega n, are 2 pi n over 2 pi n kBt over h bar. I want to put the h bars in there. Okay, so in the frequency plane, this is the complex frequency plane, the classical finite size scaling will give me lots of information on these points. And all the methods that the classical physicists invented will work beautifully at these points. So this is 2 pi t, this is 4 pi t, and so on. But this is the real frequency axis. What happens here? That's the region I'm interested in. And that can be, and it turns out that all the fancy methods, at least near the quantum critical point, all the fancy method admitted, it's in the book by Zinn-Justin or whatever, and all the bootstraps. When they ask questions about dynamical properties down here, what happens on the real frequency axis, far away from 2 pi t, they just fail completely. And I'll give you an example of that. And that's probably where I'll end. So there's still something to be learned. And there are lots of open problems here, even for this very basics, strongly interacting quantum system. The very simplest Ising model you can think of has some highly non-trivial dynamics, which I can't really read off from what's known from the books that have been written on the 3D Ising model and its finite size corrections. Okay, So let me give you an example of a basic property, and that'll be about where I end. Okay, so I had a phase transition here. This was described by the 3D. I have described this phase transition at GC is described by the 3D Ising, classical Ising model. So at zero temperature, I'm actually golden. If I want some property at zero temperature, like the ratio of the Higgs mass to the disordered mass, that's a zero temperature property. I can just open the books, and there's a paper by Brizan where I can look up this correction that I needed after some work, but it's there. Or I can call up my quantum Monte Carlo specialist friend, and he can just simulate the 3D classical Ising model and get that answer. Unfortunately, my Monte Carlo person cannot work in real frequency because of the famous sine problem. So my Monte Carlo person still today cannot give me very reliable answers down here at low frequencies smaller than temperature, which is quite easy to access in all of these experiments. All right, so I digress. So this is the zero temperature, but just 3D classical Ising. Now I go to finite temperature. So let's imagine I raise the temperature a little bit here, where the symmetry was broken. So there's no reason to expect that the symmetry gets restored immediately, so except in one dimension. Now I'm assuming I'm in two. In 1D, the phase diagram is a bit different. You immediately restore the symmetry in one dimension. So this is 2 or higher. Okay, so there's a region of broken symmetry, and eventually that symmetry will be restored by thermal fluctuations. So there will be some critical point, some TC, which will vanish at the quantum critical point. And so now, here's a subtle point. The way TC vanishes with some exponent nu. This nu is the nu of the 3D Ising model, because it's a property of this critical point at zero temperature. On the other hand, if I look at how the correlation length diverges along this line, that will also define a different correlation length exponent. And that will be the correlation length exponent of the 2D Ising model, which was computed by Onsager. In fact, that's nu equals 1. So this nu is not that. But if I looked at very close to this black line, if I looked at what's going on, I'd be perfectly happy to use the Onsager solution to get all the exponents and so on. Okay. All right, so that's one very subtle point, that the phase transition itself at finite temperature is of a different universality class than the phase transition at zero temperature. So there's a little window, I should have drawn it here, which broadens a bit where you see 2D behavior. But as you go to zero temperature, the window of 2D behavior disappears. 2D classical behavior disappears. Okay, so how do I think of it? Think of all of this physics. Well, the way you think about this physics is by some kind of general scaling argument. So you have a critical point here that has 2 relevant perturbations. One is G minus GC, and the other is temperature itself. So you can write down some scaling form. You scale everything by temperature with and use some general arguments to write down omega over T, Ck over T. And this defines the exponent nu, because temperature, remember, is just a finite size in the time direction, so it's like a length. And so that's why you get the correlation length exponent here. Anyway, okay. So let me get to the main point of the lecture, which is what's happening in this pink region. So in the pink region, the so-called quantum critical region, you sit at the critical point, or slightly away from it, and then you raise the temperature. So this is precisely, you have infinite correlation length at zero temperature. All you're doing is turning out a finite size. So there's no other length scale except temperature itself. That's the only scale you have in the problem, because the critical point is scale invariant. That's the only scale you have. And so here, you're going to get some, these quasi-particles will disappear They strongly interact with each other. You're going to get a critical continuum, not so different from what you get in the SYK model, except here I can't possibly compute anything in real time. But by scaling, you would say that, okay, if you perturb the system and ask for it, how long it takes to locally equilibrate, you would say, well, it has to be over h bar over kt. And this number c should be a universal number. Okay, so that's a claim that follows from just thinking about the dynamics of this and using some scaling arguments, not much more. And it's kind of remarkable, although this was also true for the SYK model, but that such a thing happens, that you have a strongly interacting system with all kinds of energy scales in it, the J and the JG and everything else. But its relaxation time, its thermalization time doesn't depend on anything, at least at low temperatures. It's universal. So it's self-generated universal dissipation. That's what we want to understand in this Planckian system. And so the C is a number. It's a pure number. I don't know, 2, 0.7. We don't know what it is. We're trying to compute it through some tricks. And I'm hoping someday the Rydberg atoms will get good enough to measure this number C. So that's my challenge to them. What is C? It's a universal number characteristic of the Ising model. And so neither theory nor experiment can compute it yet. And let's see who gets there first. Or really, both will have to work together because we don't have any numerical method. I keep talking to my friends who do this to, why don't you compute C? And they try it for a while and they say, no, it doesn't converge. So I don't know. Maybe if one of you will have a clever idea. Yeah. For what? Yeah, infinite system. I take an infinite system. Yeah, well, so then there's yet another parameter in the scaling function, which depends on the ratio of temperature to the system size. And yeah, it gets messy, but you can include it. Here, I'm assuming that the thermal length, so there's a thermal length, which is kind of like the de Broglie wavelength of the, so that's basically KBT, H bar C over KBT. I'm assuming H bar C over KBT is smaller than the system size. When H bar C over KBT becomes of the system size, then there's a whole other mess there. Okay. But let me just show you what the essence of the problem is. So let's just do perturbation theory. Yeah. So if you just sit down and just open your RG book, you learn 3D critical phenomena, which I don't know, in my time, this is all you did in graduate school. Everybody learned how to do epsilon expansions. Nobody does it now, right? But anyway, so I looked at all of those graphs and I just analytically continued them, put them at finite temperature. I basically just did the perturbation expansion and took the small omega limit. And the perturbation expansion was done in perturbation theory in this G, which is the basic basis of everything, that won the Wilson the Nobel Prize, the same expansion. Okay, so when you do this, you find to first order in epsilon, you get what's called a thermal mass. That makes sense. I mean, that's okay. At epsilon, there's a thermal mass of order temperature squared. That just means that equal time correlation decay exponentially. It doesn't tell us anything about damping. Okay, but then at next order, you get some damping. You get an imaginary part, some damping constant for this oscillator by computing this graph, taking its imaginary part. It's really not a complicated calculation. And then you find, first of all, it's also order temperature squared. It has to be just by dimensional analysis. But it has this very strange non-analytic form. It's sine epsilon. And that has to do with the infrared divergences in this graph. It's universal, but it's not what we think of as relaxational dynamics. What we really want is something like a damped oscillator. It should be just, the system is strongly interacting system without quasi-particles to just relax, like some quantum jelly, like SYK does. What we really expect is something linear in omega. And this gamma then would be a universal constant related to C. This is what we expect in the actual system. And this is what you actually get in the epsilon expansion. It's a sine omega rather than omega itself. So it has some dissipation, but the dissipation is not the form you expect for any kind of viscous system. It's not behaving like a damped oscillator. It should. I mean, we expect it to. Why shouldn't it? Anyway, so that's why in some way also the example of the SYK model is very revealing because it shows you clearly this is what happens. Anyway, so that's the challenge, is to compute this number gamma. All right, so what we have done in, yeah, that I already said. We're working currently, and I worked on a long time ago, some kind of semi-classical method. I think I will not go into those details because listening to 3 hours of me talk is a bit much. But that uses a little trick. It uses the trick that this thermal mass gives you is about an epsilon. This is the energy, the characteristic energy of this excitation is epsilon times square root of t. Square root of epsilon times t. Now, that means for small epsilon, the characteristic energy is much smaller than kT. Now, that is precisely the condition for classical physics. When the energy is smaller than kT, you can use a classical equation. So at least for small epsilon, the hope is you can actually write down a classical equation for phi, and thus understand what's happening in the Ising model in this region. So this was something I proposed way back when, and now we've gone back to it to look at it more carefully. This is work with Julia Way, Matthew Doddleson, and Anders Sandvik, and let's see where that goes. All right, well, thank you very much.
Questions?
So just going back to the theme of your first talk as well, how do you now understand the 2+1D transistor Ising model just above the critical point, that there will be an emergent Boltzmann type description because the renormalization of the energies are large enough that think about?
No, I don't think there will be, strictly speaking. Only for small epsilon, we think there is. So we're trying to use, but even it's some kind, what we are finding is that there are some things you can do in the epsilon expansion, but the rest you have to simulate on the computer. It's not something I can just give you an answer in the epsilon expansion. So it's some kind of hybrid epsilon method. But we definitely need small epsilon even for this hybrid method. Is there a method, maybe we're going to put epsilon equals 1 in the end. And is this going to work in 2D? I don't know. The only way we'll know is by comparing with some experiments. Or maybe there'll be other theories. I mean, it'd be great to have. Basically, all I can say on general grounds is the characteristic frequency is order kT. It's a Planckian's frequency, and for that, I know I cannot, classical expansion is not fully justified. It may be justified simply because the Bose function is already pretty much dominated by omega much more than kT, so it may have a certain 20% accuracy or something. But is it the full answer? No, I don't think so.
About the diagram that you had about the 2D Ising model. So you have the quantum critical regime. What exactly indicators you have that this regime exists? Because you said
That this is what, sorry?
If you go to the second to last diagram that you had here. Okay, so
yeah.
the critical regime, what do you have that you have analytics that it exists, numerics, because you said bootstrap doesn't work, Monte Carlo doesn't work.
Yeah.
How do you find it?
Well, I'm saying you can certainly see this crossover in all kinds of static properties, no problem. You look at correlation length, thermodynamics, anything, you'll definitely see crossover. There's no question about that. You can even simulate it, and you can see the
only
it's the dynamic properties that are hard. The real-time dynamics. The thermodynamics and equal time properties, no problem, or zero frequency more precisely.
So why does Bootstrap doesn't work?
Bootstrap works for thermodynamics and other things.
Or, yeah, okay.
Bootstrap works for zero temperature properties, and at finite temperature, there are a lot of papers just in the past year or two on finite temperature Bootstrap. That will give you a lot, but it doesn't give you the dynamic. It won't give you tau relaxation. It'll give you other things.
So what will give you the dynamics? If
I don't know. That's the open problem. We don't know how to compute C by any method. That's what I'm saying. This particular number, or this C is kind of defined by, it's more strictly speaking, this function has poles in the complex frequency plane, and where those poles are at zero momentum. They're the analog of what are called black hole quasi-normal modes. And so the black hole quasi-normal mode frequencies are what I want at zero momentum. Or even if there's actually, maybe there's a whole bunch of poles like a Christmas tree that you get in holography. If you try to get the black hole quasi-normal mode, the analog of, there's no black hole here, but the analog of the black hole quasi-normal mode frequency, Bootstrap doesn't work, and epsilon expansion and large N expansion, none of them work.
We have time for one more. So one more clarification question. So we started by discussing the phase transition from disorder to checkerboard, which you said is the generalization to 2D of the 1D transverse field Ising model transition, right?
So it's in the 2D transition.
Exactly, because you still have the SSB. But now that you do 2D transverse field Ising model, you have a Gates theory, right?
No. Well, I mean, it's dual to an Ising gauge theory, but why bother? I'll just work with the direct representation. It is dual to 2+1D Ising gauge theory. That's even harder to solve. This is much easier to work with the direct representation.
I'm sorry, I do not understand. So the model that you study is a Gates theory or not?
It's not.
You study the dual, which is not.
You can study the dual if you want. I didn't study the dual. It is dual to a gauge theory, but that's useful for sometimes. It's not, but this is the model I'm talking about. I mean, everything I'm saying, this is just the phase diagram of this model in 2 dimensions. This is the model. This is not a gauge theory. You can do a Kramers-Vonnegut duality of this model, and then it's a 2D, 2+1D Ising gauge theory. It's a Z2 gauge theory. That's much harder to work with. This is much easier. But you could work with that, you'll run into the same difficulties. Yeah. I mean, the 2+1D Ising gauge theory is, it's an order disorder thing, and at the zero temperature, fine. But the epsilon expansion is, everyone does it starting from this. I don't see how to do it from the gauge theory side. Nobody ever, it's much harder. Yeah.
So sorry, maybe you said it, but I kind of missed it. Do you have a prediction for the critical amplitudes? So the f of x that you
Yeah,
before,
you can do that with epsilon expansion. Yeah.
So, but that matches the ones of this experiment or not? That is
It does roughly match, although Anusha is questioning whether we should even use that theory, but it seems to be, in the same ballpark. Yeah.
Okay.
But I think those experiments definitely need to be done more precisely. They're much more excited about doing quantum computing, but hopefully some of them will come back to this experiment. So it's hard for me to motivate them.
Right. Can I ask which part of the phase diagram did Lukin probe in his experiments? And what kind of signatures did they make? Like what kind of
Yeah,
parameters
so
did they measure?
okay, let me just say that here. So in the experiment, at least when I matched, they're going here from across here at some temperature, I don't know. But I basically looked at what happens here versus what happens here. I think they need to do more careful work to see what's happening in the middle. They haven't done that. So they looked at here, and that's what led to, yeah. So this plot here as a function of this axis, as you go here and here, that plot is going across from here to there. Well, they do, but I haven't presented data and they don't have any accuracy to really say, yeah. I know that he's moved to Weizmann or some, he's in Israel now and he's setting up a whole new apparatus to study the pink region. So at least convince one of the Rydberg people to study that.
You made this scaling argument here for the reason for these Planckian dynamics. In the absence of a scale set by G, it has to scale
Yeah.
like this. Is there anything that makes this specific to the 2D Ising model, or is this like for any Hamiltonian if you had two
Well,
non-commutative?
So in general, scaling, it gives you various length scale. Now, if suppose I apply it as a 1D Ising model, I can apply scaling there too. But there what happens is that that model doesn't thermalize. Okay, so there exactly how it thermalizes depends on irrelevant operators. So that'll bring in new energy scale. So the assumption here is that this model, this critical field theory, obeys eigenstate thermalization, or it's some field theory that thermalizes on its own, okay? That's an assumption, not proven. Given that assumption, then I'm pretty sure this is correct.
Thanks.
But that's why it's very special. I mean, for other quantities, there's no doubt any thermodynamic quantity, the scaling works. But does it actually work for relaxation time? I think it does, but we don't really have proof.
Maybe I allow myself a last question.
Sure.
In terms of how to compare theory with experiments. I mean, the experiment is done in a box, and there is a sizable part of the box that is close to the boundary. Do you expect boundary critical behavior to be relevant here or not?
There was some of the observations in that complicated phase diagram. There was some sign of boundary behavior too. Yeah, we had some papers on that, but I don't remember the details. I mean, this is not, by the standard of critical phenomena, this is pretty primitive, but it's a start, I would say. Their correlation lengths are not, this is it's like 10 lattice spacings, and this is the actual system size. They can do much bigger now, but they're building quantum computers. There's not much money in studying this, but
So in terms of theory developments, I mean, one can try to do epsilon. I mean, I think epsilon expansion is going to be hard, right? To do it on open boundary conditions, right?
again, for imaginary time quantities, there's a lot of
There is
work
also.
and of course, there's been a lot of interest on boundary critical phenomena recently, a lot of progress in that. Max Mitlitsky and others, I think they could study a lot of that here also. Yeah.
Good. I think now we can thank Subir again. We reconvene tomorrow morning at 9 o'clock.
Oh, yeah, so that's because it's so incomplete. Yeah, but yeah, so that's why. But what it does have is only there's a whole bunch of. Eventually. That is because of very small. That's what. Yeah. So the way we say is eventually. Scaling dimensions must be then what happens in it's about a sphere. General true that again. Ising model you don't extend. No one's ever mentioned, you only measure, okay, the first five, first five. Want to go to 100 operator and see what. Telling you. And that's where you'll get some information. Yeah, but you have to be in the scaling level. So, yeah. Yeah, so they've been doing some of this, and I've written some papers on thinking of what the density is. Another crude way to say it is the FYK model is a ground, the black hole down to zero temperature. Down to the lowest energy. But the Ising model is a threshold. Something called the Hawking peak. Integral for it. Sort of like and then once the energy level. No, but again, it's a question of infinite system is not arbitrary, energy is stable, no question. With finite system, then there's a question of, then you get the low-lying operators, which are.
But this you can make it, you can do
Yeah.
this experiment on this one.
At which rate?
Ground state plus like first state. And
So how you're scaling your L with the size of the box?
yeah.
I think you have to go.
Single particle
I think you have to look at
excitations.
energy is much bigger than 1/5.
But I'm saying I can already tell in
Maybe.
this one you translate it. But I-
Could be, okay, that would be, to look at, yeah.
We don't think that.
But there's not very much known, I mean, Yin Chen has gotten, Bootstrap got like 3 or 4 operators, he's now got 10 operators. So we can only be level, getting more of a sphere, he's got. Great to look at some statistics of those. But we only have one sample. I don't know what the statistics, but yes, I think that'd be interesting to see how eventually it's got to go, what you put the system on a sphere of radius r. Then there are a bunch of levels which are some number divided by r for a while. When this number is about a 1, much greater than 1, then there's so many levels, it becomes exponentially dense. In fact, we know exactly what it should look like. It's E. That's the density of levels.
Right.
This is where I expect random matrix statistics. It has to get really dense, but I don't know what happens in between.
Yeah, in between here, it need not be as rigid as you drew it. This could be the average
these
level
are not,
spacing.
yeah,
They're not, but
but
they
the
are.
average level is sudden, or we don't really know how the transition happens.
You're right, for me. to
In
know what-
supersymmetric theory, there's a first order transition, sudden transition in the large N level. But it's some crossover, how that crossover happens.
But
you
you
know.
need for me, I would talk about a time.
Yeah, so that's, the problem of neutral black holes in the entropy is very much connected to this issue.
I think I sent you this.
Okay,
Don't know if you'll think about it.
well, how does it, there's still the out of time autocorrelation function showing maximal chaos, right?
We have examples where those would show maximal chaos and
Okay, all right.
it's on your lecture thinking.
Uh-huh.
Yes.
Okay,
Hamiltonian interpretations of integral. Like, Lots and lots of conservative.
Okay.
And the ones that are most sensitive.
Okay,
Words I can say that,
all right.
very different.
Okay, can you compute the DOE?
The NC,
Yeah.
I don't know, but I like.
Okay, good. I look forward to finding out more. Hi, hi. Oh, yes.
I'm working with her on,
Okay. Ah.
like she's told me.
Well, I'm on a thesis committee, so probably got it at any point, but I'm on a lot of them, sorry, yeah. That's all.
Just working on like that.
Uh,
She's trying to recover it. It's a still Ising model.
Right.
So I'm curious about like what.
So this is you're looking at the integrable model or then the guiding to non-integrable?
There's this machine.
Oh, yeah, I remember that, yeah.
And obviously then this. How do we use integrability?
Unfortunately, I'm leaving right after lunch tomorrow. I've been here for 2 weeks already. There was another school last 2 weeks, so I'm more on matter things. Yeah, what's your name?
Maeve.
Maeve. Okay, yeah. It's not self-dual. So the dual, as I mentioned, the dual is the Ising model, so it's not self-dual. No, in 1D it's self-dual, it's not self-dual. Ising gauge theory in the two. Yeah, that's what we discussed. Yeah, so that's why we, other representation can be useful for something. Because it's not self-dual. That's from duality. 1D, from duality, you can say a lot of things, you can know any critical. Yeah, right, that's my favorite number.
Did you say you expect?
Well,
Ising
yeah, well, no, any quantum phase transition between two gap phases where there's a broken Ising symmetry. All of those models.
He is the Ising.
Yes, I mean, but there's a corresponding, you could take the ON model and for each n there'd be. They're already on they should be on the, I've uploaded them to their file, and they should be on. Oh, you were also there, okay. Something different there. Actually, my last lecture had some of. Sure. Yes, I did. Your father-in-law. When did he graduate from Joseph's? That we only went up to 10th grade in those days.
All the way, but I don't.
I left in 76, 10th grade.
No, he may have had a reputation.
Who was the principal when he was there? Hedwig DeCosta?
Yeah. Hedwig, father.
Cop, he was known as Cop.
Was he?
Yes.
I remember him calling father.
Yes, yeah, okay. I certainly overlapped, but he was there for a while, but I did overlap with
He
Hedwig.
told me that. was.
Well, was he a boarder? I wasn't a boarder. I mean,
Yeah, he was a board.
yeah, so the boarders were kind of got to know each other very well. I had to commute like 45 minutes each way.
Had to ask.
Oh, yeah. No,
Uh,
what is the last name? Fernandez? Yeah, that doesn't, it's certainly not my class. I'm in touch with all of my classmates on WhatsApp. Even today.
I can one day think of finding. Doing things like that.
Yeah, okay, good.
But, yeah. Sensor networks would probably not work very well.
People have been trying, yeah, but I think Yahoo tried something and then he gave up. Without me. Anyway, I'm the first speaker tomorrow, so. Where are you at?
I'm at Cornell.
What's your name?
Darren, sorry.
Darren. Okay. Oh, okay.
I do a little bit of work with the button.
Oh, wonderful.
All right.
Oh,
Quantum dynamics using classical shadows. Every time I come to him saying, I think it's not gonna work, we leave, but, no, it should work. Go figure it.
okay. Yeah.
Not quite there, Peter's still